All right, in this video, we're going to quickly run through our notes for the naming and writing units formula. One thing we want to do is make sure that we review the difference between ionic compounds and molecules. Biggest thing for this unit is that we're going to identify ionic compounds that start with a metal, and molecules are all nonmetals. Ionic compounds are transferring electrons, where molecules share them. You got to think about those cations and anions. For those, okay? Also recall that the metals on the left are always going to be to the left of our stair-step line on the periodic table, so we should be referencing that as we do these things. The most important step to naming compounds is to determine if you have an ionic compound or a molecule. So again, that idea of a metal is the most important thing. If it has a metal, then we have an ionic compound. If it does not start with a metal, then we use molecules, okay? We're going to start with molecules as our first reaction type that we're going to name. Again, no metals. Yeah, obviously you can see that's pretty important as we can go through that as we look at these, okay? So when molecules work, molecules can share electrons in more than one way. They can do like a 1-to-1 like carbon monoxide, or 1-to-2 carbon dioxide, a 2-to-1, a 1-to-3, a 1-to-2, 1-to-6, lots of different things. The big thing is the same two elements, carbon and oxygen, can do it more than one way. So because of that, we need to use prefixes, which are listed here, to tell us how many of each thing that we have. Now, when we look at these prefixes, if we want to write the names from formulas, so if I give you a formula and I want to write that name, there's some rules that we're going to follow to do that, all right? So first, we're going to identify the name of the symbol for each nonmetal, okay? So we'll look them up on our periodic tables. We're going to write those names down in the same order. The second word, we're going to take that last syllable off and write IDE instead. We're going to find the right prefix based off the subscripts in the formula, which we'll find over here: mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. And then a couple little notes that we have is after you place the prefix on that nonmetal, do not use prefix mono for the first word. And if you see any double vowels like o, I drop the double vowel because that is not what we like to see. All right. A lot of times students struggle a little bit for how to change that second word. So here are all the nonmetals that we might be using and how you convert the original word that they have to their second word. So oxygen becomes oxide, phosphorus becomes phosphide, and so forth. Okay, so you could use this slide as a reference to properly change that word as you need to. Okay. Best thing we do for these is practice this, all right? So we have 6 of them here, and I'll kind of talk through them before I show the answer on them. S is sulfur, F is fluorine. I'm going to change fluorine to fluoride, and I have 2 sulfurs, so this would be disulfur. I have 4 fluorines, so this would be tetrafluoride. Okay, so together we get disulfur tetrafluoride. The di meaning 2 on the sulfur, the tetra meaning 4 on the fluorine, but I changed my prefix to fluoride. Okay, down here I see 3 oxygens and 8 nitrogens. So I changed nitrogen to nitride, and I would use trioxygen octa for 8 nitride. Here I have 1 silicone. I have 7 bromines. So I'd have silicone hepta for 7 bromide. Notice how I don't put the prefix mono on the silicone. Now I have 5 chlorines and 9 carbons. So I'd have a pentachlorine nona carbide. Here I have 6 phosphorus, and I have 1 oxygen. Even though there's not a 1 listed here, that still means 1. So here I do want the prefix, so I have 6 for hexaphosphorus. The mono prefix is needed for that oxygen monoxide. Okay? And the last one, we have selenium with 3 iodines, so it would be selenium triiodide on there. Okay? If you flip it around and you're going to write the formula from the symbols, it's the exact same rules, but they're written here for you can read through those or pause it if you need to. But let's go to that practice. Okay, so here we have carbon monoxide. So I use a capital C for carbon. I have mono and oxygen or oxide, so I have 1 oxygen on this, so it'll just be CO. Here I have 3 sulfurs, and I have penta for 5 bromines, so I'd have S3Br5. Here di is 2, I have phosphorus. Hepta is 7 for chlorine, so I should have 2 phosphorus and 7 chlorines. Make a note that this is Cl, this is not a 1 or an I, this is an L for chlorine, okay? Tetracarbon nonafluoride, I'm going to have tetra for 4, nona for 9, so I'm going to have 4 carbons and 9 fluorines. Arsenic does not have a prefix on it, so I know it's 1 hexaiodide for 6 iodines. octa for 8 carbons, deca for 10 sulfides. We have C8S10 for this, okay? So that's how you name molecules. There's lots of practice that we have in our notes. If you go back to that worksheet number 1 on molecules, you could do a lot of practice with that, okay? If you have an ionic compound now instead of a molecule, it's going to start with the metal, so we're going to learn how to name them. With ionic compounds, we do not use prefixes, okay? Because there is only one ratio that is possible. So with ionic compounds, because they are transferring that electron over, we have one valence electron from the sodium heading over to that chlorine. It only can be a 1-to-1 ratio for that +1 and -1 charge, okay? A simplified way of looking at this is to actually look at the charges, which we have discussed in previous units on how to make this compound, okay? Here's our steps, though, to kind of work our way through it. We're going to write the metal first with its valence electrons. We're going to write the nonmetal second with its valence electrons. We're going to find that ratio between them that creates 8 for each, and then use that ratio as a subscript. So here, the ratio is 1-to-1, so we get that, okay? Here's some more examples. For example, we have calcium chloride. Calcium has 2 valence electrons. Chlorine has 7. So calcium is going to want to give one of its valence electrons to each of the chlorine, as you can see here. And as a result, calcium becomes a 2+ charge. Chlorine fills up its octet. Each one is a 1- charge. So it takes 2 chlorines to balance out the 1 calcium. Okay. Here's probably the most complex one we'll see, where you have aluminum having 3, but oxygen needing 2. So the least common multiple between 3 and 2 is 6. So aluminum is going to give 2 of its electrons to one oxygen, 1 to the next. This one's going to give 1 to that oxygen and then 2 here. We can see that happen in the diagram where all those electrons go. And as a result, everything has what they want. Aluminum gave away its 3 electrons like it wanted to. Oxygen, each oxygen could gain 2 like it wanted to. So it's a 2-to-3 ratio, and we end up with Al2O3. Okay. Now, this is a lot of writing, a lot of drawing to do, so there's actually a faster way to do that. The faster way allows us to use the charge to simplify this process. Okay. So in that case, we're going to write the symbol for each element with the metal first. And then we're going to recall the charges that we have. So remember, all of our group 1 are +1, group 2 are +2, group 13 are +3, group 14 metals are +4, 15's group 15 is a -3, group 16 is a -2, and group 17 is a -1. So with these charges, what I can do, instead of having to put a bunch of dots and valence electrons, I can write the charge on each of my different things by finding them in their group. So I'll put my magnesium, I'll put my nitrogen, I'll put my charge, and then I just need to have them trade places to figure out the right number we have each one. So if I have magnesium with a 2+ and nitrogen with a 3-, that means it takes 3 magnesiums and 2 nitrogens to make this compound. Okay, so we just basically switch places here, and if you have to, you can reduce it. So if you have a 2 and a 4, or a 4 and a 4, or a 2 and a 2, you'd reduce it down to its lowest possible ratio. You do not include the charges with them, just the number as you do that. So here's the practice now for these. So we have lithium oxide, and if we take a look at lithium oxide, lithium has a +1 charge, oxygen has a -2 charge. So we move the 2 over and the 1 over, and we end up with Li2O. Okay. Strontium arsenide, strontium's a 2+, arsenic is a 3-. So again, we just switch the 3 and the 2, and we get Sr3As2. Aluminum is a 3+, fluorine's a 1-, so we switch the charges, and we end up with Al1F3. Calcium's a 2+, oxygen's a 2-. So since they're both 2s, if we switch them, it's 2-to-2, which we have to reduce down to 1-to-1 to be correct. So make a note of that one. Hydrogen's a 1+, nitride is a 3-. So again, if we flip the charges, 3 goes over here, 1 goes there, it's H3N. And then tin oxide, tin is a metal that's in group 14. So that one is going to have a 4+ charge, which we may not remember necessarily. Oxygen's a 2- charge. So same thing here again, we have a 4+, 2-. So if we switch our charges, we have a 2 and a 4, and we have to reduce that down to a 1 and a 2 for that, okay? So a little bit of practice on writing the ionic names for those. Now, if we are going to flip this around and maybe have to write the names from the formulas, this is actually really easy to do, because all we do for these is we change the second word to its "-ide" ending, which we know how to do already, and we don't use prefixes, because K2O is the only way potassium and oxygen can bond, so you don't need to put prefixes on here. So K2O would just be potassium oxide. NiCl2 would just be nickel chloride. Notice how there's no prefixes being used, but the second word is returning to ide. And if we do that for all of these, you again see how even though there's 2s and 3s and 4s in here, none of that is shown on this because we're doing ionic compounds that do not use prefixes here. Okay. The last thing we want to talk about is what happens when we have a complex ionic compound. So some ionic compounds, the second part of that ionic compound deals with multiple nonmetals together. Okay, so we're going to have more than 2 elements. It will always be one metal still. Okay, so we always can count on the fact that we have one metal, and then we're going to put 2 or 3 nonmetals acting as a group. Okay, the trick to these is realizing that group of nonmetals is acting as one thing, and we call them polyatomic ions. So it means poly meaning many atom ion put together. Okay, when that works, they have a single charge for the whole group. If you go to your periodic table, you're going to find a list of these polyatomic ions and what their charges are in the back of the periodic table. So all we need to do for these is name them the same way we did ionic compounds, but instead of having a single element as the metal, or the non-metal, sorry, there's just going to be a group of them, okay? And we just put parentheses around them. So magnesium here is our metal. ClO3 is a group. We'll just put parentheses around it. And if we need more of them, we'll put things on the outside, okay? So all those rules end up being the same. We have magnesium, and if we look at the back of our periodic table, we find ClO3, and it's called chlorate. That's the name of it, ClO3. Don't need to change anything, don't need to modify anything. So we just say this is magnesium chlorate, okay? Here are our polyatomic ions. You will not need to memorize these. You can look them up anytime you want. But we just need to know that NO3 is called nitrate. And it has, as a group, it has a -1 charge, okay? Hydroxide is OH, dichromate is C2O7, that kind of stuff, okay? So when we write the names for these, if we say CaCO3, all we need to do is say, okay, Ca is calcium. We go back and look up CO3, and CO3 is carbonate, so we would just call that, okay, calcium carbonate. I would suggest going through each one and putting parentheses around them if you do not have that already, like you see here in red, okay? You're not going to see parentheses written around them normally unless there's a 2 outside of that, but I would definitely do that for all of yours as you're working through it, and it will not be wrong if you do that, okay? So calcium carbonate. Well, here we have sodium, and we have NO3, so we go back, and NO3 right here is called nitrate, okay? So we have sodium nitrate. Here we have Fe, which is iron, and PO4. If you look up PO4, it's called phosphate, so it's iron phosphate. Here we have silver with SO4, which is called sulfate. Here we have copper with SCN. Notice how it's always one metal, and then a group, everything else is in that group, called thiocyanate, okay? So that's how we would name these. All you need to do is write the metal name down, and then look up what the second thing is called. That's it. There's no prefixes, there's no changing anything, it's really simple, all right? The little bit harder is going the other direction, okay? So if we have aluminum nitrate, how do I write that formula? We do all the exact same things, but one thing that's going to help us is that second word will end in ATE, so we know it's a polyatomic ion, okay? So in that case, we just look up when we see the ATE endings, nitrate, we look it up and say, oh, nitrate is NO3. So we have aluminum, it has a 3+ charge. Nitrate has a 1- charge, so we would put our parentheses around the nitrate, and because this is a 3+, this is the 1-, it would take 3 of those to do it, okay? So let's work a few out. So lithium is a 1+, acetate is C2H3O2 with the 1-. So we have this, but you could also write it without the parentheses. Calcium nitrate, calcium's a 2+, nitrate's a 1-. So we're going to have a 2 outside of that parentheses for the nitrate, for doubling that. Potassium's a 1+, sulfate is a 2-, so that 2- will have to be written over here, so we have K2SO4, or you could put it in parentheses also, okay? Gallium is a 3+, phosphate's a 3-, so one of those each will work. Magnesium is a 2+, and borate is a 3-, so it's going to take 3 magnesiums for every 2 borates. Notice how it's the exact same process we did for simple ionic, except for the second thing is a group instead of a single element. So we just need to find that group, put them in parentheses, and if we need more of them, put the numbers outside like we did before, okay? Now that's pretty much it. Now, if we end up mixing them up, we just remember this simple rule to figure out which naming system we're going to use. Ask the question, does it contain a metal? If it is no, use your molecule rules and use prefixes. If it is yes, then you ask yourself, is it simple or complex? Does it end in IDE? And then it is simple. It ends in ATE, it is complex, okay? So this is kind of like our check system to know which set of rules we are using when we name these. Thank you. Last thing here, we have our kind of table to help us out. So if we take a look and fill this table in, this is everything that we already know for some different examples of we have with this. And if we look, we have sodium nitride. Does it start with the metal? Yes, it does. It ends in IDE, so it's simple ionic. Here's the formula. Okay, here we have carbon disulfide. Does it start with the metal? No, it does not. Ends in IDE, it's a molecule. Here, does it start with the metal? Yes. Here, no. Here, yes. Here, yes. Here, yes. Here, no. Here, yes. Here, yes. Okay, and then down here, we see Br2, so there's no polyatomic ion, so it's just simple. Here it ends in ATE, so it's complex. So this is your basic rules for this table to help you kind of organize your thoughts on that, okay? So remember, if it's a metal, it ends in ide, simple ionic. If it's yes with no, it's a polyatomic ion, okay? So that is the end of the show. Thank you.